All right, hi everybody. As I'm answering your question and starting this, good to see you all again. We have a very short lecture in slides on, let me share screen just a moment. Okay, very short on supernovae and dark energy, and then the rest of the hour we'll do by completing a very cool exercise, very useful stuff on analyzing data. Right? We're going to analyze data. And so we'll take more time on that. And fortunately, this time I don't have to show many slides. Supernovae, I guess, only formally belong to large-scale structure. They are not usually thought as part of a large-scale structure subject. They are, of course, supernova. The objects are part of the large-scale structure. But this I want to use as the opportunity to learn how to handle any data set. It just doesn't have to be only a supernova data set. So here, let me very brief version is this mini lecture about basically the discovery of dark energy and what it is. So dark energy, dominant component in the universe, more dominant than dark matter. Dark energy known for 2 decades now, dark matter for about 80 years, if you go back to Zwicky in the 1930s. And of course, baryonic matter, but even that is only 1 fraction stars. So stars are a very small part. Dark energy, the result of the finding of dark energy, just to jump to that, is if we live here, and this is a time axis, very much logarithmic, matter falls off as 1 over the volume of some chunk of the universe. Radiation falls off even faster. Early universe used to be radiation dominated. I mentioned yesterday the matter radiation equality is about 50,000 years after the Big Bang, redshift about 3,000. Universe is now just barely dark energy dominated. Dark energy to dark matter is about 3 to 1. And in the future, presumably, it's going to be completely dark energy dominated. This domination of dark energy, recent domination and emergence we saw in both geometrical measures like distances and also in the fact that it slows down the growth of structure. The objects used for discovery of dark energy are type 1a supernovae, which are thought to be, not completely proven yet, cases where white dwarf accretes matter from a companion star and hits the Chandrasekhar limit and undergoes thermonuclear explosion. It's been recommended, it's known that every such explosion is about the same. Approximately each explosion is the same luminosity. That is to say, it gives approximately the same amount of power. And people many years ago, going back to authors in the 60s and 70s, at least they suggested that they can be used as so-called standard candles, because if you know the intrinsic amount of light to the luminosity, and you measure the apparent amount of light, the brightness, how much light, then you can infer the distance. Here's a popular talk level explanation. Imagine you have a bunch of cars at night, and you only see their headlights. You don't see them other than the headlights. You don't know for any one of them if you have a small car nearby or a really big car, say a truck far away, right? Like you can be a weak source of light nearby or a strong source of light far away. But if somebody tells you it's one in the same car, for many cars you see, then your brain immediately converts to their relative distances. Because if you know each one, then you can just measure relative distances. So supernovae measure relative distances. This is a very good analogy with cars. You don't know what car it is. You don't know how much power, but I'm telling you, you're looking at 100 of them and it's the same model of a car, the same kind of light. And then you can immediately tell me this one's closer, this one's farther, by what factor. So supernovae measure relative distances. To put it another way, if you have 100 supernovae, how many measurements do you get? You effectively have 99 measurements because you're doing relative, right? So you can do 99 ratios out of 100 data points, right? So that's the kind of thing you get from supernovae. And so really, the other thing is they're not quite uniform. This is, it's really their absolute, this is really should say luminosity, their absolute, the amount of power they emit is not the same for every supernova, but it turns out that there is empirical relation, so it just happens to be true, that the ones that go up and down faster, like this one, are intrinsically dimmer, and the one that go up and down slower, so see this green one is happening on a faster time scale than the one on the top. And so This is a one parameter family of curves that astronomer called Mark Phillips discovered in the 1990s, and he didn't get a Nobel Prize, but he could have gotten a Nobel Prize for this key insight, because you can make them better standard candles. They weren't all the same intrinsic, luminosity, absolute magnitude, but after you make this correction, you say the ones that are narrow, I know I should bump them up, and the ones that are taking a long time, let me bump them down. Then you get a very good standard candle. And now that all is one thing, but the real heroic work in this field was done by these cosmologists, so leaders of teams, 2 teams, 3 people here, who used world's largest telescopes and arranged observations so they're guaranteed to get supernovae, because if you look at one galaxy, you will have to wait 100 years to see a supernova go off. So, writing a proposal to Hubble Space Telescope to, wait 10 years or 100 years is not a very good proposal. So, but maybe if you look at 1,000 galaxies and come back to each one, you see 10 per year, and you see the pattern. And then, because you need to catch these supernovae early on their time curve, if you see it at the maximum, it's too late. You have to be able to map this light curve in order to correct for this rule, in order to correct for brighter is broader, right? So in order to correct for that, you need to measure these points well before the maximum. This whole, by the way, this whole up and down takes about a month. So people often say wanting to discover supernova 4 days after explosion. That's well before still this point, which is maybe 15 days after. All right, so here's a movie, here's a galaxy, and this is a supernova going off, and you can see a real supernova here. And it's, you didn't see anything, that gets brighter and then dimmer. Let me run it again. So its supernova went off, and you can see how spectrum evolves as it goes on the light curve. So you want to get points spread around this peak. People have done that, and this is my kind of user-friendly version of the real data. So here, every data point is binned. So there are more supernovae than shown, but each data point is an average of about 20 supernova. And today we will also use with a bin supernova. So maybe in the data set, there are actually 500 supernova, but they're binned in 40 bins. There are 40 kind of averages. And here I have a different kind of binning, and each data point is the average of 20. But you can see that this is a log of a distance. That's like apparent magnitude versus redshift. These curves, the one that's favored is the one that accelerates now, decelerated in the past. That's the universe of dark energy. All of the cases this is for like popular talk, all of the cases of matter only open, flat, or closed are disfavored. And the one that always accelerates, first of all, that wouldn't form any galaxies to begin with, and that's disfavored by the data. The one thing here that's very, very important to emphasize, I'm going to explain this in a moment, is that each curve is free to slide up and down. The amplitude is unconstrained. So, these green curves are below, but you're free to shift them up. But if you shift them up, you see their shape is wrong, right? The shape has to be like this. So it's only the shape of the supernova data you have, not the amplitude in this magnitude plane. And that's exactly the same statement as saying that you only measure relative distances. Okay, that's the key thing with supernova, relative distances. I did say this was going to be previous. So this was discovery of dark energy, and that led to these are now kind of obsolete. They're 10 years old, but these are graphs where supernovae were discovered. This is omega meta omega lambda plane. They are above 0, right? So some dark energy density, in this case cosmological constant, is greater than 0. And this is the analysis for which I said, not from this paper, but in the original paper, they did this both frequentist and Bayesian way, and they got, the data is good, you're going to get basically the same kind of ellipses. And if you relax the notion that this is lambda, you can introduce equation of state. We talked a bunch of it at this school, and then you can constrain an equation of states consistent -1. So I want this to be short. I could spend a whole hour talking about this, but I won't. But here's a really important graph slide, and I lifted these equations from my lecture notes that I want to go through with you. So please take a minute here to follow along. So astronomers' favorite thing is distance modulus, which is the difference between apparent and absolute magnitude. And this is kind of nice. It gives the explanation for a physicist. So apparent magnitude is like minus log of a flux. and absolute magnitude is minus log of luminosity. So absolute magnitude is like luminosity, it's the thing in watts, it's intrinsically how much it's emitting. And the apparent magnitude is like flux, it's like what you measure. So distance modulus is the measure, that's a measure of distance. So distance modulus, this difference is equal to 5 log base 10 of. So this line is the same as equation as, you know, flux is equal to luminosity over 4 pi distance squared, right? That's effectively astronomer's version of that equation. Okay, so you'd like to measure distance because that has cosmological parameters. Now, follow me along here. This is going to be very important for us. I can do some basic algebra. I want to take you through it. I say apparent magnitude is absolute magnitude plus this, right? So little m is absolute magnitude plus 5 log 10. But I split up immediately this and I write it as 5 log 10 dl over a different number plus whatever I, you know, 10 to the log of 10 to the 5 is or something, 5 10, log 10 to the 5, 25. So I just split this off in 2 parts. Maybe that wasn't important. This is one important line. So it's absolute magnitude. And I want to divide and multiply by h naught because combination h naught times luminosity distance doesn't depend on h naught. Remember, dl goes as 1 over h naught. So if I do this, this is just that integral dz over stuff. And then, of course, because I multiplied, I have to subtract this, right? I have, you know, h naught, and then I still have this thing. So now this is a term I really, really like that has all cosmology. That's that term plus a new parameter called script m. And script m is whatever was left over outside of this nice distance. It's absolute magnitude minus log of a Hubble constant, but in dimensionless, so it's times distance plus 25. So here the grand final formula for supernovae is apparent magnitude, which you measure, which is basically the flux, minus log of a flux, is equal to a thing that has cosmological information. So this doesn't have Hubble constant here. Remember, this combination doesn't have a Hubble constant. It has all omega matter, omega lambda, all that. And then the nuisance parameter, that's a combination of Hubble constant and absolute magnitude. Now, a very important point is now, therefore, your parameters for the analysis are omega matter, omega lambda, maybe W, whatever you want here, and this script m parameter. There's one nuisance parameter. That's a parameter you don't particularly care about. Now, a lot of people, including professionals in the field, when they write papers, they misunderstand this. I can't tell you how many papers I refereed when there was a basic confusion, basic and I would say catastrophic confusion by the author on this point. And there are many different ways to get confused here, but the result is simple. There's only one nuisance parameter. And so the standard supernova analysis is not sensitive to Hubble constant at all, because Hubble constant is infinitely, this parameter you can determine from the data. The data will tell you the amplitude, but you have infinite degeneracy between absolute magnitude of supernova and Hubble constant. So even if somebody told you that Hubble constant is some number about 70 plus minus something, it wouldn't be helpful because you still don't know this number. This number, you don't know the absolute magnitude of supernova. You just don't. So for our analysis today and for the standard supernova dark energy analysis, this is the bottom line. This combination is infinitely degenerate. You can never separate between capital M and H naught. They come in this combination. This is a nuisance parameter. You don't care about it, but you still have to take it into analysis and you have to marginalize over it, integrate over it in the end in order to get posterior on omega matter, omega lambda. One additional thing to know is there is one way to get at both capital M and H naught at big degeneracy, which is if you had a chance to measure absolute distances. If you just think about measuring absolute distance, this is absolute distance. Like really distance, somebody told you this object is, 5,000 megaparsecs away or something. Then you could do immediately measure flux, right? Measure, absolute distance, and you can get capital M, and then you can get that. You could resolve this degeneracy between these two. This happens from the distance ladder type measurements. In the distance ladder, you have a host galaxy with a supernova that also has a Cepheid, and Cepheid, their oscillations give you absolute distance. So if you fold in absolute distances, this is in fact the way people measure Hubble constant from the distance ladder. Okay, so that's potentially confusing, right? The only way to get at either Hubble constant or this is through absolute distance measurement. But the standard supernova only analysis, no Cepheids, none of that, no distance ladders. Supernova only analysis is quite clean. And you don't need to know Hubble constant because you need dark energy, omega matter, and the other. So today we will use basically this formula. We'll use this formula today. I will provide data, supernova data, measurements on magnitude, and the error bars on this apparent magnitude. I'm not telling you anything. The right-hand side is just like theory, right? So we're going to determine parameters on the right-hand side, but we couldn't care less about script m. It's going to pop out, but we don't care. It's some number like -20 or +20. It's dimensionless, so it's a random number. But we're going to constrain these parameters. So we're going to have data, the magnitudes, and actually not even the errors in magnitudes. Will have the full covariance matrix, so n by n covariance matrix, because the supernova measurements are correlated somewhat. Yep, that's it. Short and sweet, as I promised. And here are some readings. This is a very popular level reading, but very nice a Scientific American issue from 2002. It costs like $9. It's a bit on the popular side. And the other two are completely self-serving because they're mine. This is a pretty standard semi-technical review, so you should be able to follow most of it, written in an easy to understand language. We aim this article to like an astronomer, you know, not the cosmologist, that they can understand. And this is a more modern, this is updated. And one thing we did in this review paper is have compare old data and new data and have this kind of time evolution of data and how it goes. So these are the reviews. If you look at the PDF version of this, which should be already posted, you can click on these links and it should take you to the archive. So I'm going to pause here now and see if there are any questions. Let me find the right window. But I think I'm still online because I don't think I dropped out, but I lost my window.
Dragan, I see that there are some questions on the chat.
Oh, I see. Okay, I see how to. I'm gonna stop sharing now. And yes, there's okay. So I figured this out. Okay. B band doesn't matter. It's one of the bands in which you observe. It's not too important for this argument. Yeah, photometric system. Thank you, Nico. You cannot get absolute magnitude from the light curve. This is so, Reggie. If you're asking how do you know that broader is brighter, so it's always a question: how do you know the real, let's say, luminosity in that case? You know, and then always you use some sample where you practice, where you know the right answer. This is always in astronomy, right? How do you calibrate something? Let's say you have some set of supernovae, I don't know, to which you know the right answer, and then you can practice this broader is brighter curve because you need to know the intrinsic, right? This comes up all the time in astronomy. You know, how do you know something? You know, some empirical law between the two things. Well, and you're going to use it. Well, how do you find it in the first place? You had some golden sample of objects for which you kind of knew the right answer, subsample. Yeah, Mariana, this is an important point. You absolutely cannot get H0 or big M from the standard, you know, excluding this going to distance letter, which we don't use in the standard cosmological analysis. So let me just see where your argument, and if you want to speak up, you can, because I think a lot of people would be confused about this, you know. So you're saying they provide redshift, and from there one doesn't know deal, because you do literally have to go back to this. This is why I like this kind of, let me share. I think it's worth, and then you can think about it later. And if you think you have a counterexample, I'm more than happy to go. So here's supernova analysis. So you're saying, okay, so you have this depends on redshift distance, right? So I measure the apparent magnitude, and the key thing in the original equation, if you think about it, is that I had to multiply and divide by H0. And once I multiplied and divided, by H naught, I have H naught is tied up with this capital M. If I didn't have capital M unknown, I think you'd be right. If I didn't have capital M, I would say, I have some function in the theory, it has H naught, it has omega matter, so H naught is the same as all the others. But the reason H naught is not the same as all the others is I can add it and subtract it, like here, right? So I can multiply this term by, multiply H naught here, so I have a combination that doesn't depend on H naught, and then subtract it here, so that's fine, except now, unfortunately, I have two things, capital M and H naught, and I'm only sensitive to their sum. So it's like having A plus B only in your equation. If you have A plus B and then A plus B cubed and then e to the minus quantity A plus B, you can never solve for A and B. You can only measure combination A plus B, right? So here, this combination, capital M minus 5 log H naught, travels together, and you can never break it. And that's now the only place where H naught enters, because H naught, remember, this doesn't depend on H naught. That's why you multiplied. I hope this helps. Okay, let me stop sharing here and see if that hopefully made sense. Any last questions before we go to the code? Yeah, this is a very, very important point. Admittedly, it's not an obvious point, but I've refereed, I don't know, I should have kept a track of how many papers where this basic thing gets confused right off the bat, you know. And then, and just to give you an idea, if you fix that script M parameter versus vary it fully, it's not an infinite like mistake, but it's about a factor of 2 mistake in the final error bar. So like if somebody whispered in your ear, hey, script M is this much, you can fix it, meaning Hubble constant and absolute magnitude fixed. You would do a factor of 2 about bettering cosmological parameters. So it's a pretty big effect. Okay, so let's move on to code now. I have nice code, and as I said, I hope you need those files so you can follow along with me. You can try to open, or you can sit back and watch. And we don't have to finish this today. In fact, I'm going to finish this chunk tomorrow and then do more different kind of code. Share screen. Yeah, this is the one I want. If there are questions, feel free also to speak up. If you so now we have time for this. Feel free to speak up, and if I'm not showing something right or you want something to show, feel free to speak up. So, and I have to decide how big of this to show. I don't know if somebody has suggestions. So I have some usual things that I did last time. All right, so this is going to be a bit boring. I run this, I'm going to run several boxes. That's also, this is just preliminaries. This is to make plots look nice. It's kind of a self-imposed, and now I noticed it's a bit slower. I don't know if, Google should be infinitely powerful. So I wouldn't think that people being there at the same time would slow things down, but I don't know. This is taking a bit longer than I'm used to, but let me wait a few more moments, because I do have to click on this to select my file. And while it's doing that, let me see here. Then I'm just going to have just distance formula. Distance here, distance integrand, 1 over E of z, and then I'm going to have RZ. And notice here, RZ is actually distance times H naught, right? It's distance times H naught because I don't have 1 over H naught. So this function, I should have called it better. I should have called it H naught underscore R or something. All right, let's see if, well, let me see. This is not really budging, but I have a feeling this won't work if the first thing didn't. So, okay, that's going to be the distance. I'm going to be patient with these. And then here, I'm asking you, so this is our master formula, right? This is our master formula. So I'm asking you here, you can get started on this to, first of all, our RZ function, R of Z, right? H on R of Z takes Z and omega matter and omega K. And here I just want to call Z omega matter and omega lambda. Actually, RZ calls, RZ looks at, it calls Z omega matter, omega K, and W. And W, I'm just going to fill it. I'm going to fix it in stone to -1. I'm not going to vary W. So I'm asking you here to fill out this line first and then complete this line, because I don't want H naught R of Z, I want H naught DL of Z. Maybe because my zoom is slower, yes. No, stretch and color, Tiziano, is they have to do with the astrophysics of supernovae, so they probably don't know about H naught. They probably don't know about H naught. Yes, you're asking a more advanced question. There are some other parameters to marginalized over, which, you know, there are a few other nuisance parameters that are less important than this, and I didn't restart runtime. And there is a factor 1 plus Z in DL. Yes, thank you, everybody. You are being very helpful. Okay, restart runtime. How does one do that? Runtime. Restart runtime. Okay, very good. Very good. Natalie there, I think. Oh, and then I'm supposed to run this, I think. Yeah, there's no wage. Oh, okay, here we go. All right, sorry. This is a self-imposed injury, right? Self-inflicted injury here. I'm a sucker for styles. So there, I got myself a nice style. I'm going to run these distances. Thank you, Natalie. That was a very good hint. And yep, so yeah, here, well, this is not, you know, it's 1 minus omega matter minus omega lambda, right? And the only thing is you have to sometimes wonder, is it minus omega k this or is omega k this? There's like plus minus, at least I have a plus minus confusion about omega k. Oh, this is the right answer. All the omegas in the standard convention add to 1. So omega k is 1 minus minus minus. This is hard-coded. And then this is indeed 1 plus z times H naught R of Z. So R of Z times 1 plus Z is DL, and this already has times H naught. So that's that line. So I should be good there. And yep, that's that. Yeah, I'll assume that's clear. And then here we have for M theory. So this is, I need to code this up. This is theory. I'm going to compare to data, but theory is 5 times numpy times log 10. It's log 10 is log base. All the logs here are base 10 for this magnitude from astronomy convention. And then I do this DL function. What was it called? Oh, it's not called H naught of Z comma omega matter comma omega lambda. So I call this function I just defined. It's 5 times log that. Oh, right. And then let me note plus script m, right? So I literally call this up, right? So that's really the hardest thing here is that slide, the understanding that script m is a nuisance parameter. It's a sum of 2 other nuisance parameters. So we're actually saving ourselves information by lumping 2 unknown things into 1. Okay, run that. That's good. That was easy. Okay, so this is a bit of a pain. You have to load data. This chunk didn't work for me. This way it works. So you know, I'm a bit new to this, but you click on choose files, you click on these 2, and you do open, and it should do. And then just to see if it works, it's reporting here dimensions. Oh, I didn't run the box, right? I was supposed to run it first, I think. I was supposed to run it. And now I think it's waiting for me to select these 2. Okay, it's happy. And it says that data is 40 long and the covariance is 40 by 40. So those 2 files, you can look at them also. I think you can click here and then look at, oh, I made some copies. I was suffering here greatly earlier. And there on the right side of the screen, I don't know if you can see it, you can see the data. It's a list of redshifts and magnitudes. And let me not worry about it. You're going to have easier time looking at it. So these are bin supernova. There are actually 500 supernova, but somebody was kind enough to average them just because I want smaller files here. It's not a big deal. We will need inverse of a covariance matrix. I inverted right on the spot. We could have inverted 500 by 500, no problem. The other thing is, this is another way to do it, and then you have to get some confirmation code on Google Drive. I'm new to this. It can also work this way instead of this. It didn't work for me out of the box, whatever. I hope you can get this thing to work. It's accessing files. Okay, so now we have a list of redshifts, 40 redshifts, 40 average apparent magnitudes. So you pretend you have 40 better supernovae instead of 500 normal supernovae, right? You have a list of 40 redshifts, 40 apparent magnitudes, and 40 by 40 covariance matrix. Well, we need to analyze that. This is a basic statistic. So first we plot it, and I think I am, so I did this for you. So first of all, you could guess that a model where omega matter is 0.3, this is M theory of when omega matter is 0.3, omega lambda is 0.7 will fit well. You still need to specify in that model script M. And script M is like completely kind of a weird number. It's dimensionless, but it's a sum of logarithms or something, right? So logarithms always give weird answer. So I did this for you. I did a little search earlier over script M's to find which one is the best fit for these two parameters. I didn't say these two parameters are the best fit. They are just ones that I think should be good fit. And this one I just kind of optimized for you. And so when you plot that, it shows supernova data. This is a bit smaller than shows the data points are data. The orange line is the model. And the amazing thing, the error bars are being shown. So the error bars are pretty small. The reason is partly because these are averaged points, so the error bars are a bit smaller, but it's only part of the reason. The other part of the reason, this is actually a pretty big scale. As those of you who like astronomy, you know, 1 magnitude is quite a lot, right? 1 magnitude is a lot difference. And here you have 10 magnitude scale. So on that scale, these are pretty small. And just to make sure this is, you always want to do sanity checks. Here, I kind of did this for you, but when you do this, you say, wait, where are the error bars? Are they hiding? Let me multiply errors and using this plot.errorbar function where you can give the errors. Let me multiply them by a factor of 10. And when you multiply by a factor of 10, you can see the error bars, at least here at high Z. At high Z, somebody was asking earlier, there are fewer things, so it's easier to see error bars because there are fewer supernovae here. So they are there, they were just hiding, but I'm gonna, you know, the plot goes to there.
I have a question.
Yes, go ahead.
Which database are you using for this plot?
This is Pantheon data, Pantheon. It's currently like the dominant, most popular data set. If you Google Pantheon supernova data, you will quickly, one of the top choices is a GitHub repository. There you can find bin data. It's not quite in this super nice form. There are some other columns, so you have to clean up only for the columns you want. But it's the Pantheon supernova data set from a variety of surveys that they combine supernovae from. Some are old, some are new, supernovae observed.
Thank you.
Other questions? Let's see, this is a good place to stop for questions.
Yeah, I have. Some of us are getting like data is shifted compared to, well,
Yeah, I've been getting a lot of that earlier today, but I'm not anymore. So of course, as always, it's a bug somewhere. So now you have to go and find how far they shifted.
Well, this is like the model is -40 and then the data is around 20. Like if you just take the vertical, not the vertical, the horizontal axis, the y-axis.
Sorry, this should be like going from 15 to 25. Where's your other line going from to?
Okay, I can't share.
You can share.
Okay. Can you see my screen?
You shared your whole screen, so you should at least put at the back. Yeah, that's, oh, okay, yes, that's, yeah, so this is a simple bug. In fact, this is easy to explain. Just go back a little bit, go up a little bit, and go up where you did mem theory. So I think there's a called mem theory. So you did minus script m in your M theory. It should be a plus script m. You see on the bottom of that box, you have that should be a plus. Yep, that should be a plus. And now it's gonna work.
It's skewed.
Oh, now there's another problem. Okay, go up. let's look at your M theory. So this is the rite of passage, this debugging. I actually kind of like this. So 1 plus z times rz. Yep, that's correct. Yeah, so you have np.log. That's natural log. You want log base 10. So it's np.log 10. And I don't know if that's enough. Try again and run that box and the two below.
There we go.
Okay, good.
Oh, thank you very much.
Yay, yes. You know, I'm a big fan of programming, and partly I like it. It's a big emotional ups and downs. It goes from despair and hating your day that's all gone to great victory and scream, you know, and these ups and downs, they're kind of nice, except when you're at a real low. But yes, I've even
I think
experienced
you described
programmers.
everyone's life.
Yeah, bugs, yeah, everywhere. So
Thank you very
okay,
much.
good. So let's so feel free to keep asking questions, everybody. Let me get back at it. That was pretty easy stuff. Okay, so hey, so that best fit model, is it a good fit? So calculate chi-squared and report chi-squared between theory and model. This is, okay, you know, one of the most basic statistical. So give me a chi-squared between theory and model. And what helps is that this ampersand sign is multiplication in Python 3, and you don't even have to worry about the transpose. So chi-squared is normally data minus theory, or theory minus data squared divided by error squared. But here we have a covariance matrix. So we want to form a combination here. So my observations are called, I can do one or the other. My M obs is my vector of observations. Minus, and then I need the theory, and it's called M. So it has a weird name. It's called M theory array. So it's just creating array for every Z redshift and Z obs, it's creating a value of M theory. So it's doing minus that thing. Okay, so that's the vector. I should have that transposed. It just happens that I do Python 3. I don't need to do .t. So it's just this, miraculously this works. And I'm gonna have that at the end also, right? I might as well copy it. And the order matters, as you know, with data matrix multiplication, order matters, obviously. And I think I call that inv C, right? So I'm multiplying a vector. This is a row vector. This should be a row vector times matrix times column vector. And again, somehow it's smart enough. It doesn't even need to take transpose of this. Normally you will take a transpose here. So M obs minus M theory transpose times inverse of the covariance times this. This is your basic expression for chi-squared, right? With the diagonal covariance. And I print that and it gives me 44. Now, I have a question. I got 44. Earlier today, I was getting 150 for a long time. And yes, I went with that emotional up and down. It was first anger, then disbelief in some order, and then it was a victorious thing, not the biggest of bugs. But I do want to ask people here, is this, okay, so this plot, it's too hard to see by eye. Everything is closed. It's model data in theory are closed, but the error bar is also tiny. So I could zoom this up, I won't. But is it a good fit? And let me see what the chat says. Oh, I see this scroll down, yes. Oh, zoom in, yes, I can zoom in. Yeah, what's the critical chi-squared? Somebody saying it should be around 40. So, okay, so does somebody, what should be, what's a good chi-squared? All right, so you get chi-squared. Chi-squared should be comparable to the number of degrees of freedom, because remember, chi-squared function, as I have in the chat on Slack, has for n degrees of freedom, the mean is n. the variance is 2n, right? The mean is n. So it should be close to n. It's usually not much smaller. It should be much smaller or much bigger than n. So here I have 40 data points. Do I have 40 degrees of freedom? Well, right now I do have 40 degrees of freedom because I didn't fit any parameters. Had I fit 3 parameters, I would have had 37 degrees of freedom. Usually these two numbers are close. You have many more data points than fit parameters, usually. But here I actually didn't fit any parameters. I just picked 3. So it doesn't matter. Number of degrees of freedom is 40. So chi-squared should be ballpark 40. It could be 42. It could be 44. But if it's 75, it's probably wrong. And I had it 150 this morning. I knew something was wrong because I knew that my model wasn't going to be, it isn't a terrible model, you know, especially because I optimized over this. So 40, it should be around 40. If the chi-squared is 20 or some smaller number, there's still a problem. That usually means you overestimated error bars, okay? But that doesn't happen so often. Most of the time you get high squared, which means either you messed up or the model is a terrible fit. So 43.9 is great. That's in the ballpark of 40. Okay, so I'm very happy with this. Now define log likelihood. You want, this is a Gaussian likelihood. It's a 40-dimensional data space, right? So this is a Gaussian where the covariance is 40 by 40 and all of these vectors are 40 long. And why is likelihood okay to be Gaussian? Because remember the central limit theorem. Thanks to that, most of the time we can assume it's Gaussian. So here I started to, we want log ln, really, natural log of this likelihood. So first of all, I'm telling you if omega matter is ever negative, and p, by the way, is the parameters we want. So our 3 parameters are omega matter, omega lambda is script m. That's going to be in our analysis. Omega matter, omega lambda is in the distance, and script m has to go for the travel. I'm telling you, if you ever feed in that likelihood negative omega matter, just return like infinitely bad result. But other than that, because you fed parameters here, so z obs is unchanging. It's always the same set of redshifts corresponding to my data, right? And m obs is also unchanging. What's changing is theory. So here I feed in theory. P is theory parameters, and I want to get log of a likelihood, ln of a likelihood. So what's ln of this likelihood? Well, ln of that likelihood, if I say, first of all, d is going to be this for me, m minus m transpose. So d is going to be the same thing I had here, actually. This is going to be my d, right? So it's just, I just want to make my life simpler. So I'm just creating this combination because in the likelihood, I can say d, then this at inverse c. So at d, and I don't even have to worry about transpose as usual. So the same thing I did here, except I don't know, I just like clarity. So I define this as d, and I don't need parentheses here, even this d. Okay, so this is log likelihood. And so inverse c, remember it's calling inverse c, it's calling z obs. It knows about them because they are things, quantities that exist outside, so it knows about them. So I don't need to pass them in here. I want to pass to control what parameters I'm passing, but these things are kind of fixed in stone and it knows about them. Is this correct? Let me look at the chat. Okay. People help me find bugs in this. Do I have any bugs? What do I have obvious bugs? I want ln of that likelihood. You can speak up also. Minus 1/2. Thank you. Thank you, Nelson. Minus 1/2 matters, especially being minus. So I forgot that. What about the rest? Does this matter? This chunk. Right, okay, Zhao. So you're right about that. But this whole thing, so here's an important punchline for this part. I could code up minus log of this. It doesn't matter. Because if you think about pure constant like 2 pi, multiplying the likelihood by a constant or adding a constant to a log likelihood makes no difference in the analysis whatsoever. Whether you multiply all likelihoods by a constant or add a number to logs doesn't matter at all. So 2 pi does not matter whatsoever. What about that of the covariance matrix? That's a number, and that also is not changing. So that number is not changing because covariance doesn't depend on cosmological parameters. Because covariance, this determinant is some number. It's a hard-coded fixed number in this whole problem. And I can treat it just like 2 pi. It doesn't matter. But if covariance depended on cosmological parameters, if somebody told me, hey, here's a function for covariance on cosmological parameters, I know because I ran a million simulations on a big supercomputer and I checked it out, then you do have to change. So you only need to include things that depend on cosmological parameters. So here can ignore covariance because it doesn't depend on any of the parameters P. Does that make sense? That's an important point. Yeah, the -1/2 matters because multiplying a log likelihood or having a number in the exponent, this is, putting -1/2 here is not multiplying likelihood the number, right? It's square rooting the exponent. So that messes up everything. The only thing it's insensitive is if you double all likelihoods. But this is not multiplying all likelihoods. This is doing square rooting the exponent is not the same, right? So this is then messing things up all over the place. It's just changing things. It's only insensitive to overall amplitude differences, overall amplitude in likelihood, if you multiply all likelihoods by 2 pi or something. So equivalently here, if you add a number to this, it doesn't matter. But if you multiply this by a number, it doesn't matter. Okay, moving on. So that's my log likelihood. Now, the crown jewel of this analysis, sampling, and I'm going to start this today and end tomorrow. We have 3 cosmological parameters. We're going to do Markov chain Monte Carlo Metropolis-Hastings sampling. So to remind you a little bit about that, let me remind you what we've had. We had yesterday we had MCMC. Remember, it was based on okay, so I hope everyone's looking at MCMC slide. So MCMC's, this Metropolis-Hastings algorithm says you had some model, you make a proposal to go to some point, make a proposal, the length of this step should be ballpark estimated error in the cosmological parameters, ballpark, okay? And if you're going to a higher likelihood, accept always. If you're going to lower likelihood, form a random number between 0 and 1. And then if that random number is less than your ratio of new to old, accept. If it's greater, move. That is to say, if you go to very, very, very small new likelihood, your random number would have to be just really close to 0, which is unlikely to move there. So most likely you won't go. While if you kind of go just slightly lower likelihood here, it's most likely you'll move because your random number should be between 0 and 0.9 or something when you pick it between 0 and 1. So then you'll move. Okay, so that's the Metropolis. And then I remember I ran this movie yesterday showing in this 2 dimensions.
We're not seeing this that you want us to see. We're not seeing the screen you want us to see.
Oh, you're not seeing the screen. Okay. Which screen are you seeing?
We're seeing the collaboration, the collab screen.
Oh, sorry. Oh, sorry. Okay, now?
Yes.
Okay, sorry about that. So if you go to higher likelihood, you always move. And if you go to lower, then you throw a random number. Sorry, I was waving my cursor, nobody could see this. But if you go to very, very low likelihood, that random number would have to be very close to 0. So you're unlikely to move. If you go to just slightly lower likelihood, then that random number could be, say, for example, between 0 and 0.9 when you pick it between 0 and 1. So most likely you are moving. And so that kind of turns out that recipe, which is 3-4 lines of code, ensures that's Metropolis-Hastings, right? So you have to code this up. And this is how it looks, right? So you propose, you're going to lower likelihood, stay, propose, you're going to lower now, was rejected. It could have been accepted, was rejected, try again, turns out it was rejected. There are random numbers at play, right? go now, rejected. And so as you are rejected, you increase the weight at that point. Weight is how much you stuck around at that point, right? That's your weight. So eventually you have a file with each line is a model where you spend, and either you spend almost no time at it, you moved on to the next model, like this model wasn't very popular. But this model was very popular because you were just rejected a lot of times to move from here. So therefore, that was a pretty good spot to be. So this is what we need to do. Let me share screen here. Sorry, I'm trying to not get confused. But I need to. Oh, exercise 3, right? Yep. Okay. So I hope people can see the main screen again. If not, let me know. And well, we have to do MCMC. What should our steps be? Here's I'm providing more length. So I'm saying, yeah, try these numbers. Okay, these are about the good numbers. These are numbers you try. Just try these numbers to try stepping. In a professional code, you would first try some numbers, then learn roughly, very roughly what constraints will be, and then update these steps. But you're doing these steps. So you're going to be stepping in this 3-dimensional space. We're only going to do 3D. We won't do 10D or 20D. But 3D is already nice, just to set it up. So first you want the proposal function. And here I'm not asking you to do anything. It would be a little hard to ask that. So I say you propose a step for parameters P. So remember, P is this triplet. And you say return P plus a step, but I want like a random number. So pick a random number from a Gaussian distribution. So that red arrow in that movie is this quantity. It has lengths of this much in 3 dimensions, but each one of these I multiply by a random Gaussian number. So this is some Gaussian that's between, well, it could be any number between minus infinity and plus infinity, but most likely it's between minus 0.01 and 0.01, right? So it's a Gaussian with width 0.01 in this direction and Gaussian in this and Gaussian that. So I'm kind of random, right? You want to step randomly in 3D, where the typical excursion is this. Are there questions about this line? So these are the three steps. Okay, so this is the proposal. I'm going to use this. Now, the heart of the MCMC. You step, and you can start from this point. It doesn't really matter where you start. I'm starting from this point. I'm not saying this is the best fit. It can be really any point where you start. You could start at, just don't start at a really bizarre point, like at, I don't know, omega matter of 10 or something. Okay, you want to, within reason, somewhere where you're still not disfavored. And then count, just follow that algorithm, okay? And I'm asking you first, just do it for a few steps, like 10 steps, okay? And then you'll do 10,000 steps. That'll take like a minute. And then eventually, maybe at home, you'll do 100,000 steps. So I'm getting this started off for you here. And I am, step size could be uniformly distributed also, Joao. Yes, Gaussian versus uniform is one choice. Yes, yes, it could be. That's the answer to your question. All right, so I'm, some of these initializations you don't want to suffer through. So okay, so this is the parameter array to start with. But the main thing here was really my declaration that it's going to be array with 3 elements. Okay, and so these are initial values. And so you see, I can remember this is ln of p. I'm going to just do 10 steps initially, and then later 10,000, etc. And then this is going to be chain. I'm setting it up to be 0. So this is the values of 3-dimensional length n, comma 3 for the for which parameter values. So these are parameter values, and then these are likelihoods corresponding to the n steps. So in this case, I'll only have 10 steps. This is something I'm going to talk about tomorrow because we're going to talk about weights. But first, I want to get started here. So, okay, this is a mode sign in Python. This is saying if I is divisible by 1,000, so every 1,000th step, tell me I'm doing 1,000. Because when I run 10,000, I want to see how fast it's going. So I have a parameter as point P. Right now, P remembers these values. I want to propose Q. So Q, remember, is you get it from taking a P and that random step. What is LQ? Fill in here. All right. Well, LQ is, yeah, the acceptance rate. I'm going to come to it. So LQ should just be equal to log-like of Q. That was easy. Because P is, where's my log-like of P? I have a log-like of P and log-like of Q, right? Log-like is my NL likelihood. Then if I want you to fill in here and keep this rest of the line. So this part is correct. If something, this is the second part. So you're moving, when are you accepted, right? You accepted either something simple, or if the ratio of likelihoods is greater than the random number, but in the log, that means log of new likelihood minus log of all likelihood is greater than the log of the random number. So this is a random number between 0 and 1. So I do everything in log. So instead of L new divided by L old greater than random number, I do log minus log greater than log. These are all natural logs. What's the first statement? Yep, thank you, Jean. LQ greater than LP. So if LQ, and there's only that sign that I have to worry about. I'm a cheater here. I'm looking at my cheat sheet because it is hard to lecture and solve. Those of you who ever lecture anything, you will learn that quickly. So you need some unfair advantage. But either if LQ, actually turns out you don't need parentheses here, but it doesn't matter. Either if LQ is greater than LP, sorry. So, and I don't know if I needed parentheses there. Yeah, maybe I do. Either if the new likelihood is greater than the old likelihood, than the current likelihood, I'll definitely move. If it's not, then I want it to be, this is a number smaller than 1, but this is also the number smaller. This is a bit weird in the log, okay? You have to kind of take a look at what the log does. So this is the right stepping condition. Then P is equal to, is going to be the easiest line of the day. Then I update. My new parameter set is going to be the proposal. Because if I'm rejected, I'm going to stay at whatever P I'm now. But if here I was accepted to moving, so I'm going to update. My P is where I was proposing to move. So I finally move, and LP is LQ, right? And then if I moved, I count the number of accepts. I increase by 1 the number of accepts. I accepted, and I say, yay, accepted. I'm going to save this thing for tomorrow, talking about weight. And then if I'm rejected, I save rejected. Well, not much happens if I'm rejected. In fact, nothing happens. All this weight stuff I'm going to talk about tomorrow. See, here I'm saving the weights. And it's a bit of a pain. I'm kind of an amateur Python person, so I Googled the hell out of it. There's one way to do it. Anyway, I'm kind of adding weights if I didn't move. This is an important line, actually. And here, in fact, I want you to fill out something. This is just what index of this parameter. Because you see, I'm moving on. If I'm at, say, 10th step of this procedure, maybe I was accepted 5 times and rejected 5 times. So the length of this is not 10, it's some smaller number. That's where I'm counting the 10. But what's the important thing? What should I do to the weights? If I was rejected, the weights evolve as the weight at that point. Yeah, so it's not, Nico, that I would say, yes, I add 1 to the weight. And Nico, I don't add to the data. I add this so data untouched. We're talking about theory, right? That's important thing not to confuse, even when normal everyday speaking, right? Data is fixed in stone. It was somebody measured it on a telescope. I'm not touching the data. As a good statistician, you only touch theory. And so theory, I'm remembering if I'm, what do you say? If I'm rejected, adding to the data. So I'm remembering where if I'm accepted, the P is here in the weights is where I am adding information. I'm adding information where the new model is. So I'm keeping history here in this line, but in this line, I'm just, imagine I don't care about weights, I just walk around, then I just need to know momentarily what the new model is. That's this line. So I'm keeping the history here in this line. Yeah, here I add 1 to the weights if I'm rejected. And then, okay, store the next point, whether it's the same or not. Oh, right, this thing is also, sorry, also Nico, actually, this is the clear list. Accepted or rejected. I'm remembering where that point is just in case I need it. And what is likely for this. So whether accepted or needed, this is going to be some repetition here. This is not actually what I want for my final analysis. But the important part is, so you're done now, and then your acceptance rate is what? And the acceptance rate is N is the total number of steps, and the variable only ACC only when I accept it. So it's going to be, the rate is ACC divided by N, okay? So I run this once to make sure it works. And of course it doesn't.
I think you should run the above so.
Oh, above also, thank you, Natalie. You have sharp eyes. Yeah, so easy to run. Yes, you gotta run that one and then run this one. And this one works, acceptance rate is 0.2. Well, that's irrelevant because it's so. So I run now for 10,000. Then I advise you to run a few more, but 10,000 steps. So, and out of curiosity, let's see how long it's taking. So 10,000 steps, and here it's gonna be evaluating. And so you can see at what rate it's printing on. So I'm gonna wait a minute here, 1,000, 2,000. So it's actually doing quite a lot of heavy lifting because these distances are integrals. And so for each time, there's a 40 data points. For each data point, it needs distance. I'm doing 40 integrals at every model. So I'm doing 10,000 times 40 integrals, right? Is that it? 10,000 times 40. Yes, I'm doing 40,000 integrals. It's a lot of integrals to do. So that's why it takes a while. And remember, this is Python. It's not like the fastest language. I'm not getting. So here, the acceptance rate is 0.19. Well, so somebody mentioned in the chat, it should be 0.25-ish. That's right. Acceptance rate should be, if acceptance rate is 3%, it's a problem. If acceptance rate is 80%, it's a problem. So it should be something 20, 30%, something. This is great. And then, so of course that worked because I fine-tuned things that are, yeah, you can also just, yeah, okay, good. Acceptance rate, everybody's gonna get similar acceptance rate with the modular noise because you made the same choices. Now, I'm gonna just do a tiny bit and then stop. So here I have the code for you to plot the histories of these three arrays to see these three. So there's omega matter, omega lambda, and script m. And so if you are really good with MCMCs, which is really useful for jobs, you know, things like that, you can look at this, and I'm actually not an expert in this, but they need to look to, you know, wiggle, look kind of like random noise, wiggle and then move down. There shouldn't be very many long stretches. There shouldn't be like all over the place. So if you are, remember in our picture, if you have steps too high, you're getting rejected all the time. If your step, imagine you make huge steps. So you keep going to huge omega matters or tiny negative omega matters or something. So you're not moving anywhere. You'd have like a lot of a flat line. You'd have kind of a flat regions here because you're not moving. We don't observe that. If you have a tiny step, then once you add a good place, you get you stick around. You make small steps around and you like where you are. So then that also doesn't look right. So this looks about right. In order to test this, I do something. I go way back and I say, let me just bump up this step by a factor of 10. So this is not even, it's just a script m parameter. Maybe I can do this one also. I don't know, for a factor of 10. So I made steps much bigger. And just to see what happens, so I made steps very big. And maybe I'll just do 5,000 of these to save a little time.
I have a question.
Yes.
It's possible to make these steps variable. So when the code starts to converge, the steps start to become smaller. I don't know, something like that.
No, you're not supposed to change your steps. You need to keep follow the rule and keep stepping. You have an initial choice of the steps, and they're going to be random numbers, but you're not supposed to slow down or speed up at somehow by your design. You need to follow a mathematical algorithm. So you're not supposed to, you know, change something in the algorithm. That's what you're asking. You have a choice of what kind of stepping are you going to have, but then you have to continue with that same recipe for stepping. Otherwise, you get wrong results. So, okay, oh, by the way, I have a 1% acceptance rate now. So I may still get results eventually. What's going to happen is only one step in 100 is going to be. So I'm going to be very slow. I'm painfully slowly will I get to, I will get cosmological constraints that are okay, but it's just going to take me longer because I rarely get accepted. And let's see how those look. They should look sick. And yeah, they do look. So if you're an expert in this, you don't have to be an expert. You can see there's this weird trend in script TAM. It's moving from one place. It's not happy oscillating. It's kind of going from somewhere to somewhere. And these other parameters have long stretches where there's the same value. So this looks very sick. So that was just an example of why, you know, how you can kind of, it's a little bit how you can arrive at the right stepping. So I'm gonna continue with this tomorrow, but I want to say that this is, people say that Markov chain Monte Carlo is a little bit art, a little bit science. The science part is very short. It's just that algorithm is very small. But then all these things that I kind of did here for you, choosing the step size, do you make occasional big step to get to another island as we recently, especially this thing about stepping and how to efficiently move is a lot of art and a lot of kind of trying out different things and recipes to get there. So that's where you can spend a lot of time, even though the algorithm itself is just a few lines of code. Okay, let me see if there are any other questions, and people can feel free to ask verbally. Let me see, how do I get rid of this? Okay. Yes, that's a new expression, sick, yes. Yeah, Marcio, if you're getting, so all of you are getting different results, post on Slack and I'll be happy to catch your bugs, you know, very happy. That's kind of, yeah, so Tiziano is still worried about, so Tiziano, it's an advanced point that people that may depend on cosmology, some systematics, but a lot of the time, if you think about some systematic error, like, you know, the amount of dust or something, I don't know, that doesn't, why should the amount of dust in the galaxy know about Hubble constant or something? You know, it shouldn't. To very good approximation, it shouldn't. Why should some astrophysical thing, or if systematics has to do with our observing condition, weather at my observatory is always bad, you know, that for sure cannot possibly know about cosmological parameters, right? So a lot of the time it doesn't. Sometimes it does depend, but in the supernova analysis, it's a pretty good approximation to say that covariance matrix of supernovae don't depend on cosmology. In some other areas like weak lensing, it very much covariances of different things completely. It's not distances anymore. And there it completely depends on cosmology, right? But in our particular case, it turns out not so much. If you can think of, I mean, you're mentioning here, I don't know, if you can think of an example of a term that should depend on cosmology, I can pretty quickly convince you. For supernovae, it shouldn't depend very much on cosmology, like astrophysical parameters. Anything else, people? And those of you who are having bugs or issues, post to Slack. I'll be very happy to address. Post a picture of your code or the relevant part. And I think, yeah, we can continue this tomorrow. I didn't want to run overtime brutally every time. I think I told Raul yesterday, I don't feel good when I run overtime, although these numerical things take time. But today I want to make sure we will finish this tomorrow. You'll bring some questions, we'll discuss, and then we'll just, I think I will show you some, we're going to do heel picks. I'll show you like a document, not proper slides, and then we'll do some exercise having to do with heel picks and CMB.
Okay. Thank you, Dragan, for your lecture. See you all tomorrow. Thank you.
Thank you, Paulo. Thank you, everyone. See you all tomorrow. Get some rest.